Hello dear friends. So far we have looked at the common indoor air pollutants and the sources of those air pollutants. In this lecture we will look at some simple methods of estimation of emissions. Actually, estimating emissions from each type of source is a very big and time consuming task. So the aim here is to basically introduce the student to one basic method and the concept behind the method so that the student gets an idea of the method and the concept behind it, and then perform similar tasks later, or can develop these basics and conduct more advanced studies. So we will look at these basic method and one or two examples as well we will look at. So basic devices used are emission test chambers and emission test cells, and we will cover the example of VOC emissions. So according to the International Organization for Standardization, we can say emission test chamber as an enclosure where we can control the operational parameters. For example, here we have an example of how an emission test chamber may look like. So we have like exhaust fan would be there, or air inflow, ventilation inflow and outflows will be there, and the sample will be placed inside this cell, and temperature, humidity, these kind of things can be controlled inside the cell, so that we know under test conditions how is the emission happening from the product. Emission test cell is a portable device which determines VOC emissions, but now instead of bringing a test sample and putting inside a test chamber, we take the cell and put it against the surface of the wall or whatever product we are going to estimate emissions from. So the device is placed against the surface of the test specimen, and then we will measure the levels of the pollutant coming out. General test parameters during emission investigations are temperature, because that influences the emissions, relative humidity, then air exchange rate. So here the term used is ACH, which is air exchanges per hour, which is essentially the number of times the total volume of a room or space is changed in 1 hour. So 2 exchange per hour means the air inside a room is exchanged 2 times. So on an average one can say every half an hour the air is flushed out. The air velocity, the product loading rate, which is basically the ratio of the surface of the product to be investigated to the volume of the emission test chamber. So if I have a cube box and this is my test surface, so this is the surface area and we cover all the area, surface area within the room. So volume of the room, surface area of this building block divided by the volume of the chamber. So that would be our product loading factor, and then we have the standard testing conditions. So a emission test chamber, again we are here, it's the sample is placed inside and basically this is closed, so it is sealed gas tight against the outside atmosphere, so no other functions can influence these emissions. Then it can be used for estimating emissions from both surface and volume samples. So we can cover the surface, or we can put the material in some sort of a stand so that the emissions are occurring from all the sides, so the whole volume is there. And then boundary conditions, we will see them in a bit. They are selected in such a way that they may reflect the conditions typically found in indoor rooms. So could be relative humidity, could be for example the temperature. Although we may finally note that test chamber is not a real room. So while making these test chambers, we are going as close as to the reality of a room. It is still not a perfect room because a room is different and a chamber is different. So it is not perfectly possible to create the conditions inside the real room, but using such chambers we go as close as possible to what could be in a real room. Typical sizes are 0.02 meter cube, so that's very small, to as large as 50 meter cube, which is a fairly large test chamber. Generally, so the common volume is 1 meter cube, which is more or less a small size test chamber. Often the material made is stainless steel or glass. So before the emissions are happening, one would like to clean the surfaces of the chamber so that the chamber itself is not a source. And generally the material is stainless steel or glass. Then we determine the specific emission rates which are associated with the application of a product in a reference room under specified ventilation and climate conditions. So we will see a reference room is again sort of a standard room. So from emission chamber we may extrapolate to reference room and then maybe extrapolate to another room. So this is like a simplified test chamber schematics. So here we have just a test chamber which is a volume uh, of V. Now in this test chamber we put our surface from which we have to estimate the emissions. So now assuming we are covering all the surface below in aluminum foil and we are, or maybe as well as the edges, and we are only estimating the emissions from the surface or maybe the edge as well. So we have the sample surface area which is contributing to the emissions. So we have volume V of the test chamber, surface area of the surface or the building material sample from which we have to determine the emissions. So in this case the loading factor becomes A divided by V, surface area A of this material divided by the chamber volume V. So a loading rate can be considered as a standardizing parameter in which we are always looking at the ratio of the emitting surface to the volume of the indoor environment we have. Then the next thing is we will push clean air at an exchange rate n, so it will give a representation of how quickly the air is flushing the indoor environment. And then there are emissions coming, and these emissions will lead to some concentration C inside the chamber, and under the assumption that the environment inside the chamber is fairly well mixed, the all the air inside the chamber will have the same concentration C at any time t, and then this air basically goes out. So we have the chemical containing air at the concentration of Ct mg per meter cube. Now this concentration is then measured by a instrument, can be an online detector, or people can take episodic samples and then take it to the instrument and where they can measure it. So generally the reference, so now we have a mental picture of how the test chamber looks like and what exactly is going in and out and what our interests are. Now when we have reference room parameters with respect to construction products, there are two standardization committees who have given some values. One is the European Committee for Standardization, CEN. The other is the International Organization for Standardization, ISO. And this is how they give different parameters. So here we have the CEN and here we have the ISO. So temperature is typically 23 and it's common to both, and it can be considered to reflect perhaps a typical room in several environments. But this can of course be changed depending on the specific situation. But in terms of a reference room, 23 Celsius, 50% relative humidity, ventilation rate of 0.5 as ACH. CEN also defines a dimension of the room which is 3 meter by 4 meter by 2.5 meter and has one door and one window. So some sort of reference room conditions are also specified. There is no such dimension for ISO, however the volume is specified here. So this is 30 meter cube and in ISO we have 17.4 meter cube. Then we have the loading factors, meaning the surface exposed area of the emitting surface compared to the volume of the room. So in terms of walls, ISO specifies 1.4 and CEN 1.0. floor or ceiling, so the bottom and the top surface are 0.4 meter square per meter cube of room for both the uh, agencies. For small surfaces, doors and windows also there is a specification here, because here we have doors and windows specified, whereas no such specification in ISO. And then we may have some very small surfaces inside the room, so we have much lower loading factors for CE and 0.007. For ISO it is 0.011 meter square per meter cube. Then we have the chambers. So that was the reference room. Now we have the test chambers. So here we have temperatures pretty much similar, 23, but the ranges allowed are a little bit different, 23 plus minus 1, 23 plus minus 2. Relative humidity is also around 50 plus minus 5. Here air exchange rate is also specified, 0.25 to 1.5 in CEN, but in ISO we have variable, and it is varied together with the loading factor here. Then the chamber material is basically the same in both of them, which is stainless steel or glass, as we have also sort of looked earlier. Loading factor is considered to be 50 to 200% of reference room, but with a maximum value of 2.0. Whereas in this ISO, you can change variably loading factor as well as the air exchange rate. Now we can look at the process of estimating the rate. So emission rates can be defined as the mass of chemical released per hour. It is per unit time. So in our case, we have defined the time as hour. So the units will be milligrams per hour. Then we have the specific emission rate, so which is defined as emissions of chemical per unit sample surface area per unit time. So milligram of the chemical per unit surface area of the sample per unit time. So this is basically an area specific specific emission rate. So it standardizes the emissions from from any surface to emissions per unit area of that particular surface and per unit time. Generally, if we put a surface, maybe it's a new surface, we put it in a chamber and then its emission is happening. Over time, the emissions will decrease as more and more chemical vaporizes. There will be less and less possibility of more chemical being vaporized, so or volatilized. So the emissions generally will decrease from the surface. So for this time decaying concentration, so the emissions were sort of completely mixed in the chamber, and then the concentration was coming out. Now since the emissions have decreased within the chamber, the concentrations coming out will also decrease. So for the time decaying concentration, one can derive specific emission rate as the rate of change of concentration with time plus a factor related to the existing concentration divided by the loading rate, and this is the example of decay curve for VOC. At steady state, we will have SCR equal to NC by L, because there would be no more concentration change with the time. So after at steady state, which means there is no change of concentration in time, it is possible that there is nothing being emitted, in which case the steady state SCR will become 0, because there is no emissions after a very long time. Generally, the agencies have defined different times of exposure, one related to long term and one related to early exposure. So, for example, CEN, there is one measurement to be taken after 28 days, or one estimation to be made after 28 days, and this basically denotes a long term exposure. Even ISO has a similar value, 28 plus minus 2 days. Then CEN also gives the estimation at 3 days, same for ISO, 72 hours. So 3 days. This basically gives an indication of an early exposure. For example, a surface has been painted, so maybe there are more emissions in the first few days. So if we are estimating after 3 days, we have an idea of the early exposure, which actually may be larger than the longer term exposure. So one after 3 days and one after 28 days. So slight differences are there among both of them, but essentially they are covering the same aspects. A short term or early exposure, and a longer duration or after long-term exposure. We can sort of look at different parameters that may influence the emissions. Here it has been found that temperature has some effect, and it depends on the chemical, how much the volatility is sensitive to the temperature. Relative humidity of the air that is coming in the chamber and sort of flushing the chemical, but also then the indoor air becomes something of a relatively similar relative humidity. This has less effect than the temperature. Test chamber volumes do not seem to influence the emissions a lot, because test chambers generally happen to give similar SERs. However, higher loading factors and exchange rates may influence the SER estimates. So loading factor and the exchange rate generally is uh, going to influence more. Then we have interferences to emissions. So if we have a wet product, we may have a lower reading because maybe the chemical, when it is being vaporized, maybe it's being also absorbed to some of the more wet areas of the surface. So initially the emissions will be lower, but of course as time goes by, these absorbed chemicals will be redissolved. So again they will emit, because they were extra on the surface, there will be more desorption. So we can have lower readings initially but higher readings later as the chemicals are redissolved. Now, if we have to determine emissions from only the surface, then the edges and the back must be sealed. So, in this example, what they have done is this is the surface that this is the material, but they only want to get the emissions from the surface. So, they have covered the edges with aluminum foil and of course at the bottom as well. So, only one surface is exposed for emissions. Then we have something called a sink effect, which means the compound released from the substance may be absorbed within the test chamber. So the emission went out, but maybe the compound then sticks to, for example, chamber walls, um, and this has been found to increase as the boiling point of chemical is higher. Uh, Sink effects also increase by introduction of some absorbing surfaces, for example, carpet. So, if we are interested in getting emissions from a carpet, the sample itself can sometimes act as a sink. So, and then finally, to prevent carryover of estimations from one test chamber to one test to another in the same chamber, the chamber itself must be thoroughly cleaned so that we do not have legacy emissions coming when the sample has changed. So now we will look at some methods for calculation. So here we have our volume, chamber volume with the sample inside, and there is some emissions happening, and we are measuring the concentration that is coming out of the test chamber. So we are measuring C at time t in milligrams per meter cube as measured by sampling the outlet. So the emission rate and milligrams per hour can be estimated by the multiplication of C with the volume and the air exchange rate. So here we have CT in milligrams per meter cube multiplied by the volume in meter cube divided by hour. So we will have mg per hour, and it's very important to make sure that the units are consistent. This will avoid any calculation mistakes often. Also, it will make sure that there is no issues with conversion of units. Once we have the emission rate, the specific emission rate, which is area specific emissions in milligrams per meter square per hour, can be given as the ER divided by the surface area of the sample, which is being used for emission. So milligrams per meter square per hour. So milligrams of emissions of chemical per meter square of the specimen per hour. So we have now the specific emission rate for the test chamber. Now we have to extrapolate it to the reference room air concentration. So here we had the variables loading rate and the exchange rate. So concentration in the reference room can be derived as the multiplication of SER multiplied by L, which is meter square per meter cube, divided by N. So eventually you can check, the units will again be milligrams per meter cube. Now this is our reference room with the loading rate and exchange rate. Now if we were converting to another room, so other room air concentration, which will have a different loading factor in this case. So C other room is now equal to SCR multiplied by this other room loading rate divided by N. If the other room differs only by the air exchange rate, which is NR, then the C other room would be SER multiplied by L, which is the same as before but the different NR, so divided by the other room exchange rate. So now we will basically look at a couple of examples. So this example is on the estimation of specific emission rate. So here we have a chemical X which was put in a CEN reference test chamber with a loading rate of 0.75 meter square per meter cube and the air exchange rate of 0.5 per hour. And then the following observations were made for the concentration of chemical that is coming out over time, and our task is to calculate SCR. So these are the observations made. In this case, observations were made every 4 hours, 4 hours, 8 hours, 12, 16, 20. Until 4 days in this example. So maybe we are looking at the 3 days exposure. But it is seen here that the concentration in the air has consistently, it's decreasing from 25 milligrams per meter cube to 18.4, 14.0, 11.0. It is consistently decreasing and then it stabilizes at the 5 milligrams per meter cube level. Now our task is to calculate the specific emission rate. So now we have to recall here that the specific emission rate can be given as delta C by delta T plus NCT divided by L. So this is our specific emission rate for a time variable situation, not the steady state situation, in which case delta C by delta T will go to 0. So we have the SCR at any time t. So now we extend the table. So here we had already TH, we have T in hours till 96 hours. Now we add a term delta T in hours. Then we already have C in milligrams per meter cube for all the 96 hours. We add the term delta C in milligrams. So this would be change in the concentration over time. And then delta C by delta T, which is actually what we are interested in. So then we can go ahead and calculate this value. So 18.4 minus 25.0, this is minus 6.6. Now delta C by delta T would be minus 6.6 divided by 4. So that will become minus 1.65. So we will put that value, 4 minus 6.6 minus 1.65. Then we can do the same thing here. Again the delta T is 8 minus 4, so we can put 4 here. Delta C would be minus 4.4, and then delta T will become minus 4.4 divided by 4, make a dot here, equal to minus 1.65. 1. So we can put 1.1 here. So I will change this. So we have 4 minus 4.4 and minus 1.1. So we can continue the same here. Delta t we will find it's always 4 hours. So we will just have 4 everywhere. Then likewise we will keep on calculating the delta c values. So 3 minus 3 minus 2 minus 1.3 and so on. And then same way we can go delta c by delta t. So now we will just fill these values and we will have a full table on delta c by delta t, which is what we were interested in here. So this term is completed. Now we have to look at the SER term. So this one, and we basically now need to calculate this also, and using this value and this value. So we reach to step 2, which is calculation of SER. So we will use delta C by delta T from before, and now we will start calculating NCT. So we have C 18.4 and N is 0.5. So 18.4 0.5 is 9.2. So fine, we have 9.2 here. Then we can fill what is SER and then the next NCT. So in this case the SER is 10.1. Then we can calculate the next one, which is again NCT 14 multiplied by 5, so 7.0, and then corresponding SER is 7.9. So now we can populate the whole table. So we have SER as a function of time with us now. And also we can see that the final steady state SER is 3.3. The concentration has stabilized to 5. So the specific emission also has stabilized, and in this case it is to 3.3 milligram per meter square per hour. We also can now plot SCR versus time. So on the y-axis we have SCR milligram per meter square per hour, and here we have time in hours, and we can see a nice decaying function, and it looks like the steady state was actually reached within 3 days, which is around 72 hours. And when we look at the exact value, we are actually looking at somewhere around 52 hours. So the SCR had declined almost at steady state. So in this case the equilibrium was achieved relatively rapidly, uh, but and then it didn't reach to 0. There were always some lower emissions occurring. We see we started with more than 10, now we are at 3.2, but this 3.3 is basically looks to be within this time frame of 4 days being constant. So here we have another example where we are given to determine the indoor air concentrations of an ordinary, which is a non-reference room. Here the steady state specific emission rate is given, which was 1.1 milligram per meter square per hour. Loading rate is given and the air exchange rate is also given. Now we have to do 3 calculations. Steady state concentration of a non-reference room which had a loading rate of 1 meter square per meter cube, but same exchange rate. So here instead of 0.5 we have become 1. The next one, the loading rate is the same, but the air exchange rate has changed, and the third situation where both are changed. So first is concentration we have to calculate for the reference room. So here we will have CRR equal to we can write the formula SER multiplied by L divided by N. So this will be 1.1 multiplied by 0.5 divided by 0.6. So this is approximately 0.9 mg per meter cube. So I will make it in print form. So the reference room concentration, which is to be used as a reference now, is CRR equal to SCR multiplied by L divided by N. So 0.9 mg per meter cube. So that is the step 1. We have calculated the reference concentration. Step 2 is calculate the concentration in the other, which is the non-reference room. So here we have other room. SER remains the same, but here the loading rate has changed. So we will have LR by N. So this will be other room air concentration with a different loading factor, which is now 1 meter square per meter cube. COR equal to SER multiplied by LR divided by N. So now we have 1.8. Similarly, the next one is we have the same loading rate, so the L remains the same, but NR has changed now to 1. So we have SERL multiplied by NR. Divided by NR. SER multiplied by L divided by NR. So 0.55. So in this case, we have determined when N is the same and LR is the different in the other non-reference room, and here where L is the same but NR is the difference. So we have calculated another item here. Then finally, we have the concentration in other room where both LR as well as NR are different. So we have COR equal to SCR multiplied by the new L and divided by the new NR. So 1.1 divided by 1.1 milligrams per meter cube. So here we have seen basically some simple calculations on one, how to determine the specific emission rate given the observations. Then from specific emission rates, how to calculate the concentrations in reference room or a regular, which is termed as a other room, which is not a reference room. So here we can conclude the whole week. We have covered the introduction to air pollution. We have seen what are the common indoor air pollutants. Then we have also seen the common sources of the pollutants and the pollutants that are emitted from each of the source. Some methods on the restriction or control of emissions as well. And then in this lecture, we have seen the simple methods for estimating the emissions. And this concludes this week of lecture.